we'll get back started. It's been a couple days since I posted a lesson, just trying to get you guys caught up on some of the statistics stuff. Hopefully you've tuned in today to do your quiz or whenever you're looking at this. When we get to next week, when you have to do the assignment, it's going to be more like a mini version of a test, so you'll be able to print it out, write your answers in. There'll be mathematics involved in it, not like the quiz that was all multiple choice and true or false. And you'll be able to resubmit it through the Dropbox. I'll give it instructions on that. In the meantime, we have to get through the last two lessons, so 3.7 and 3.8. So there are filled-in versions of these on the on D2L, which for sure print those out and see what it's all about. There's a lot of information on there that's not necessarily pertinent to what we're doing. So I'm going to highlight the majority of the stuff that we need here, as well as the example. And as long as you can do the example from 3.7 and the example from 3.8, you'll be more than fine for the little assignment. Okay, so the idea here is so far in all the way up to 3.6, we've only been dealing with one variable statistics. So one variable statistics is when you look at a single set of data. Okay, so the average height of people in our class. That's one set of data. Okay, the next two lessons are on two variable statistics. So that's when you're comparing two sets of data. So there was a question on the quiz that talked about plant heights and the amount of sun that they get. And it specifically asked for which one is the independent variable, which types of variables were part of 3.1. So it was still an okay question, but that was actually a two variable scenario. So the idea is that the height of a tomato plant is directly affected by the amount of sun it gets. Okay, it also may be directly affected by the amount of water, but in this scenario we just looked at amount of sun and its height. So the amount of sun would be considered the independent variable, and then its height would be considered the dependent variable. Okay, in a scatter plot, and a scatter plot is something where you're always comparing two pieces of numerical data. Okay, two pieces of quantitative data. The independent variable always goes on the traditional x-axis, and the dependent variable always goes on the traditional y-axis. When you form a scatter plot, you may get a wide variety of results. So all your data could be tightly linked together, sort of like this, forming what appears like a linear relationship. And it could be one that's positive. So this we consider positive because if you were to put a line of best fit on it, we'll pretend that's straight, okay, it would have a positive slope. This one here would be considered a negative correlation because the slope of this is negative. But both of these, because the data is so closely linked together, it's considered a strong correlation. Now you can still have trends, but the data might be a little farther spread out. So this, if we were to put a line of best fit on it, would still be a positive correlation, but notice the distance from the data point to the line of best fit is farther than here, right? This has very short distances. This one has longer distance. This is what we would consider a moderate correlation. Okay, and then the last option is either a weak correlation, whereas this one, again, you could draw a line of best fit through it, but this sort of distance is very great. Okay, so it's quite a weak correlation, or you could have one where you don't see a trend line at all, and this would be considered no correlation. Okay, perfect correlation would be when they're all on top of each other, so they form a perfect line like that. Okay, now the way that we identify a correlation is by calculating what's called an R value. An R value is called the correlation coefficient. So correlation coefficient, we identify with an R, and the R value always has to be between 0 and 1, or -1 and 0, depending on whether it's a positive correlation or a negative correlation. Now the closer you are to 1 or -1, the stronger it is. So this is a very strong correlation. This might have an R value something like 0.95, whereas this might have an R value of -0.95. Okay, both very strong correlations, close to 1, close to -1. As your correlation gets weaker, it's going to go into a different range. So this might have an R value of something like 0.6. Okay, it's getting less and less. Closer to 0, this may have a R value of -0.6. And then as you get weaker, you're getting in the positive state closer and closer to 0, something like 0.2. And if there's no correlation whatsoever, we would consider our R value to be 0. Okay, so there are ranges, so sometimes you have to describe what type of correlation exists. And there are ranges. So strong correlations, whether they're positive or negative, go basically between 0.67 and 1, or -1 and -0.67. So that third of the data, basically. Moderate, between 0.33 and 0.67, or -0.67 and -0.33. And then weak to no correlation, between 0 and 0.33 and -0.33 and 0. Okay, so if you're given a graph, you should be able to identify just by looking at it whether it's strong, moderate, or weak, and you should be able to just identify by looking at it whether it's positive or negative, right? Okay, it's basically if you drew a line of best fit on it, how would you identify what the slope is? A negative correlation, positive correlation. Okay, so that's one type of question you're going to get. Can you just tell me how correlated are the data? And what that means is basically how much does the dependent variable truly depend on the independent one? Okay, and the stronger the correlation, the more true it is. So if you looked at that tomato example, hours of sunlight, height, the height is completely correlated to the amount of sunlight. If you put that tomato plant in a dark closet, it's not going to grow. If you put it outside in the sun, it is going to grow. So they would be completely correlated. Things that maybe aren't correlated is the number of times that you speed versus the number of tickets you get. You might speed a lot and never get a ticket. Okay, so you might they might not be correlated at all. They may be correlated. Number of hours you study versus your marks, that's probably correlated. Okay, there can also be negative correlations. I know one we've talked about in the past is sort of the cost of something and the number that are sold. So for you guys, if say it's the cost of phones and the number that are purchased, if the phones are in excess of $2,000 or $3,000, no one your age is going to buy them. So the higher amount of money they get, the less that are sold. So it's considered a negative correlation. Okay, so your next logical question is, will I have to calculate an R value? How do I know what the R value is? Here we guessed. Well, for sure there's an equation to calculate an R value, and it's an ugly equation, but because we're in the world of distance learning, you'll have the equation in front of you. It's just a matter of plugging numbers in and then solving. So I think in this instance, what looks like a daunting equation will actually be not that bad for you. Okay, so if you kind of follow along to the next page, we'll do the exact example they have there. It's filled in for you. I don't have a filled in version with me out here, so I'm going to be using my calculator to figure it out. Okay, but basically this question goes like this. First of all, they give us the formula for coming up with an R value, and it looks scarier than it is, I promise. N, that's the number of terms we have. We've already talked about that. The sum of x times y. So you multiply your x value and your y value, add them all up. That minus the sum of all the x's multiplied by the sum of all the y's. All divided by the square root of n, sum of your x squareds, minus the sum of your x's squared. So this is being multiplied by, same thing with y's. Okay, so that formula was on the first page, no problem. Now the example you have looks like this, and we have to make a small correction because the solution online I've made a mistake, so we'll fix it in here. A farmer wants to determine whether there's a relationship between the mean temperature during growing season and the size of his wheat crop. He assembles the following data for the last 6 years of crops. So basically he has a thing that will say what the temperature is. And then this is his yield. His yield in this case happens to be in tons. Okay, and his temperature in degrees Celsius. Okay, so his temperatures look like this. 1 year, the average temperature was 4, 1 year 8, 1 year 10, 1 year 9, 11, and 6. So he's looking at it for 6 years. the amount of crop he gets in tons, when it was only 4 degrees, he got 1.6 tons. When it moved up to 8 degrees, he got 2.4. So automatically that makes sense, right? The warmer it is in the spring, the better their crops are going to do. If it becomes frosty at some point, it's going to kill some of the crops. So he looked at his data and said, there may be other variables affecting it, and this is where we have to make the correction. The one in the note says 2.2, but when I did the calculation, I accidentally put in 2.1, so we're just going to switch it to 2.1 to make it easier. So this is his data, and you may look and say, well, the year was 9 degrees. He had 2.6, that's the most. How come he didn't have the most in the year that it was 11 degrees? Well, there might have been a frost at one point during this average temperature of 11 that killed some crops. There's other variables that may be available. We just want to see what's the correlation between these two variables. Okay, so now you have to decide, kind of the first thing you need to decide is, what is my independent variable and what is my dependent? And often something like temperature or time is your independent variable. You can't control that. Okay, you can't control the amount of time that's passing. You can't control the temperature outside. So the yield is completely dependent on what the temperature is. Now, if you had to put down here, we're only dealing with temperatures up to 11, so 2, 4, 6, 8, 10, 12. And again, this is in degrees Celsius. Yield in tons, we have to go up to 2.4, so we have 0.4, 0.8, 1.2, 1.6, 2, 2.4, 2.8. Okay, so if you wanted to just make a scatter plot, the idea with a scatter plot is you are just putting points that match. So we need to find the coordinate for 1.6. When the temperature was 4, we had a yield of 1.6 tons. When the temperature was 8, we had a yield of 2.4. Okay, you have a better graph than, obviously I'm making this on a whiteboard that's not very good. 9, 2.6. 11, 2.1, 6, 2.1. Okay, so when you actually make this, the next question is, what does the linear correlation appear to be? Okay, so if you just looked at this and you had to draw a line of best fit, the best you could, a line of best fit wants you to kind of even out the number of data points that are above the line and below the line the best you can. So again, it doesn't have to start at 0, 0. That would make no sense, right? So you just kind of draw it through the best you can. And we would look at this and say, it's definitely positive. That we can tell. That means that the yield is definitely being affected by the temperature. But this does not look super strong, right? It has nothing to do with the steepness. That doesn't matter. It's this distance away that each point is. So I would say, in my opinion, it looks moderate positive, maybe even weak positive. Okay, somewhere in between those, and we won't know until we find an exact R value. Remember, if our R value is under 0.33, it's weak. If it's between 0.33 and 0.67, it's moderate. If it's between 0.67 and 1, it's strong. Okay, so we want to assign those sort of words. So what does it appear to be? Moderate to weak positive. We're not sure until we calculate. Okay, so in here, and this is where the mistake was made when I had here, there was a 2.1. So the idea with how you're going to calculate this is I am going to erase what I did right here for a minute, which is going to make our lives easier. Everyone is able to copy that down, or if you've printed the note, it's already copied down for you. Okay, that gives us an idea of what the scatter plot would look like. But in order to use this formula, we can always set it up in a chart, because essentially what's happened here is temperature has become our X variable. Okay? Yield has become our Y variable. The things we need to calculate in this situation, if you look at the formula up here, even if you don't really understand, we need to have an X squared value. We need to have a Y squared value. We need to have sums of X's. We need to have sums of Y. So eventually we're going to have sort of a line down here that will always be the sum of things for us. Okay, so we can find the sum of our X's. We can find the sum of our Y's. We can find the sum of our X squared. We can find the sum of our y squared, and the only other variable we need is x times y. Okay, so this is sort of a handy chart. It's already, the titles are already filled in here. If you get a question like this on the assignment, just refer to this chart and put in your values. Otherwise, you do the math exactly the same. So what we would be doing here in order to solve this is I'll do all the sums at the end. I'll just calculate these. Okay, so because temperature is x, and here we want x squared, we just take whatever our temperature is and square it. So 4 squared is 16, 8 squared is 64, 10 squared is 100, 9 squared is 81, 11 squared is 121, 6 squared, 36. Not bad, easy. Okay, on y squared, you may have to use a calculator. Okay, 1.6 times 1.6, 2.56. 2.4 squared, 5.76. 2 squared is obviously just 4. 2.6 squared, oops, 6.76. And then 2.1, this is where the mistake was right here. So just make sure you catch that. Just in my composition, I did it wrong. 4.41, obviously they're both going to be 4.41. Okay, so that's one calculation. So all I'm asking you to do here, square a column, square a second column, then multiply the two columns together. So x times y. So x times y, again, get your calculator out. 4 times 1.6, 6.4. 8 times 2.4, 19.2. 10 times 2 is 20. 9 times 2.6, 23.4. 11 times 2.1. And 6 times 2.1. Okay, so we filled in the main columns, and now the very last thing you have to do is go through this row. Okay, and these are going to be the numbers you're actually drawing out. Okay, when you look in here, everything is the sum of, the sum of, the sum of, the sum of, the sum, the sum, the sum. You can't do anything with these numbers. You need to do the sum of these numbers, which means we need to add. Again, when I write a double line like this, it's a financial sort of math term, it means to add. So here I am simply doing 4 plus 8 plus 10 plus 9 plus 11 plus 6. And I get 48. And each column I'm simply going to add. And hopefully I don't make any mistakes because I don't actually have the solutions in front of me. Okay, so I'm simply adding the values that appear there. Okay, is it a little bit annoying to do? 100%. Is it hard to do? No. All of you can multiply. All of you can add. 2.56 plus 5.76. And every single time you're just adding 4 numbers. Okay, and then my last column. Okay. So as long as I haven't made a mistake here, those are all the sums. So now when you actually go about substituting it into this formula, okay, you're going to sub in what you know. First of all, the very first thing it asks for is our n value. N is the number of terms. We looked at 6 years here, so that becomes a 6. Multiplied by the sum of x times y. Here's x times y. Here's the sum of it. 104.7. Subtract the sum of x's multiplied by the sum of y's. Sum of x's is 48. The sum of y's is 12.8. That's all going to be divided by the big square root symbol in here, n, which is 6, the sum of x squared. So sum of x squared is 418 minus the sum of x then squared. So the sum of x was 48 squared. Do the same things with the y's. 6 times the sum of the y squareds, 27.9, minus the sum of the y's, all squared. Okay, so it's just a matter of actually calculating. So the numerator, 6 times 104.7 minus, in brackets, 48 times 12.8. I get 13.8 in the numerator. My denominator, I'm going to do sort of in 2 steps here because I don't want people to get lost. So here I'm doing 6 times 418 minus 48 squared. I get 204. Multiplied by whatever this is going to be, 6 times 27.9 minus, in brackets, 12.8 squared, which is 3.56. So 3.56 times 204 in the bottom, square root of which equals 26. So I now have, if I push this over, 13.8 divided by 26.95, really, if you want to put a couple extras. 13.8 divided by 26.95, and I get 0.51. Now, remember the thing about your R values, it has to be between 0 and 1. So this is exactly what we predicted. This is a very moderate positive correlation. Okay, if it had dipped below 0.33, we would have considered it weak. If it had risen above 0.67, we would have considered it strong. This is as moderate as it gets. It's right in the middle of 0 and 1. 1 is perfect correlation, 0 is no correlation. So 0.5, or 0.51 in this case, is perfectly moderate. Okay, so this is how you work this out. The formula is scary, but as long as you understand that this big sigma means the sum, it should be no problem for you to calculate this. Okay, there's a very good chance you're going to get one of these on the assignment next week. So make sure you do a couple practice ones. There's very few questions in the textbook on this stuff, but I want to make sure you know how to even make up your own question and see what you get. Okay, so that pretty much covers, it says, what conclusion can you make about the relationship? We can conclude that there is a moderate relationship between them. So in general, the higher the temperature, the bigger the yield of his crop. Okay, 3.8 is next. Thank you.